outside southwest California. That's right at the edge of the Scripps Canyon. Anyway, this is a summary of how I believe they occurred during the flood. This is not drawn correctly. In the book Flood by Design, I had an artist redraw it in the way it should be. What you should see here is the continental shelf sediments are there first, and then after they're deposited, the submarine canyon is cut down into the shelf sediments. But this artist had them both accumulating at the same time the submarine canyon was cut. Anyway, consider you had a huge amount of sedimentary rocks here. It's not drawn right. Anyway, the flow is channelizing, and as it's channelizing, it's accelerating and starting to cut the continental shelf sediments. And as it's cutting, it's forming a valley right in here, and it's a very strong channelized flow, and it's causing a lot of debris to pile up and slough down into the deep ocean, cutting a submarine canyon in a matter of weeks. And this is what they look like right in here. And this sediment forms before the canyon is cut, not at the same time. That's why it's drawn wrong. And the submarine canyon is commonly a reflection of the canyon on land. And sometimes they say, well, the river, which a lot of times comes through these canyons, cut the submarine canyon. But a lot of times, these submarine canyons go way down deep to about 10,000 feet below sea level, so rivers can't be responsible. And some areas don't have rivers, but they reflect the valley, indicating that when the valley was cut on land that's now land, it cut the submarine canyon at the same time. Then they have some ideas on how these were cut over long periods of time, but still they have lots of problems explaining the origin of submarine canyons. And here's one quote from the Journal of Geology. At present, there are a few studies of processes by which submarine canyons are initiated and grow. And further work is needed to document how self-indenting submarine canyons form and how they interact with subaerial incised valleys. These are essentially weasel words for saying we have a few ideas, but we have a lot of difficulty. It's not quite saying we don't have a clue. There's degrees of weasel words. Anyway, they have a lot of difficulty explaining these features. So in summary, in this research project of 20 years of the surface features of the Earth, there's lots of major features of the Earth's surface that can be readily explained by the retreating stage of the flood that they can't explain. Massive erosion leaves behind tall erosional remnants that wouldn't be staying tall if it was slow erosion over millions of years. It leaves behind planation surfaces that are not forming today, and it has transported boulders long distances that normal rivers wouldn't even transport 5% of that distance. The eroded sediments form the continental shelves. Valleys, canyons, wind and water gaps, I didn't talk about some of these things. Pediments and submarine canyons form rapidly during the channelized flow of the flood. Mainstream geologists have great difficulty explaining all these features with their slow processes over millions of years model. All these features are worldwide, indicating it's a global event, not a local flood. There's startling evidence that Noah's flood really happened right on the surface of the earth, right before our very eyes that we can see. So that's all I have on this topic. If you want to know more, get the book. Questions? Yes?
Right here in Colorado, as you're probably aware, we have about 14,000 foot mountains. And they're all right at 14,000 and 14,300 feet, somewhere in that range. Mm-hmm. Most of them. And I've noticed some of them are even flat on top.
Yeah, there are a lot of planation surfaces on the top, yes.
My question, are those like just the very tips of, is that a planation surface that's been just deeply eroded?
That's what a lot of geomorphologists think, that all the mountains of the earth used to be planation surfaces, and as it was rising up, it was eroding, so that in many cases it's totally destroyed, so you can't see it anymore. But in some cases it's still there, leaving flat top mountains, like the ones you see in your Rocky Mountains. You do have some in your Rocky Mountains. Whereas some of them are so totally eroded, they're more pointed and jagged now. But that could be the reason why they're at the same altitude, because it was one big planation surface, and as water eroded it, the peaks that did end up there are generally at the same altitude. That's been noticed by a lot of people in a lot of mountains, the Alps, the Sierra Nevadas. A lot of them are at the same altitude. Good question. Yes?
And I was reading, had been reading in one spot that they talked about, tidal forces. When you end up having flood, as it's just starting to drain down, that you'd end up having large tidal wave things going on. How does that crank into what you're talking about?
Not a lot. Yeah, you would have those oscillations, but the rising continents and mountains and the water rushing off would probably be a lot more powerful force. The tidal effects would probably be more significant in the flooding stage, maybe early in the retreating stage when it's totally flooded. The tidal effect would be pretty significant. It wouldn't be these little tiny 10-foot tides you have in the oceans today. From what I understand, without the breaking of the continents, acting like a brake or to stop, slow the water up in the tides, we would have, I don't know what size, maybe 100-foot tides or more. We'd have big changes. But I'd say that probably wouldn't be much of an effect compared to all the other catastrophic effects going on at the same time. Volcanism was going on at the same time, by the way. So, yes?
What effect would floating debris have with this process?
You would have a lot of that. I believe strongly in the log model. It would be, you'd probably be grounding a lot of logs in spots. Maybe that'd account for places